Topic B6 is biochemistry and the environment, the last of the standard level sections. And it starts by looking at xenobiotics. And xenobiotics are substances that we might find in an organism that really, frankly, shouldn't be there. For example, antibiotics, food additives, pollutants, insecticides, heavy metals, hormones, and plastics. So these are all foreign to an organism. And these substances can build up within that organism, and when they build up, we call it bioaccumulation. So something like mercury, we're going to see that build up in fish and be stored by the fish, which is going to have problems when we look at the food chain. So what we can find is that the concentration of these xenobiotics can increase as we move up a food chain. And so a good example of that is this insecticide DDT. It's very good at killing mosquitoes, and sort of arguments at the moment to continue using it in malarial regions. However, the DDT goes into the mosquitoes. It's fat soluble, so it goes into their systems, but it doesn't get broken down, which means it bioaccumulates. And then if we think of something eating those mosquitoes, they're eating a lot of mosquitoes, they're getting a lot of this DDT into their system. Then something eats that organism. What we're doing is we're biomagnifying what we've got in terms of that pollutant. And again, similar example with a fish. You can see here if there was some mercury in the water, each of these carries a little bit, but then something eats those, more of them. Oops, sorry, down here. We've got more of them. These fish, few fish here eating many fish here, so they get a bigger dose. This seal eating many fish, there's only one of them, they're getting even more of this mercury in their system. And finally the polar bear gets the brunt of it. So what can we do? How can we make things better? That's what amelioration means. We can use host-guest chemistry, where you are trapping your xenobiotic with something that's going to fit around it, a bit like an enzyme substrate complex, but you're making a supramolecule, or supermolecule as well, that is going to trap that substance and help you remove it. So it's important to consider what are the intermolecular forces in there that we need. Another thing we can do is we can make sure we're working with biodegradable substances where possible. So these are substances that are easily broken down by microbes. Big problem with plastic bags, for example, is you've got strong carbon-carbon bonds. They're non-polar. There's not really any chemical point of attack there. They're not very soluble, so they're hard to break down. But if we introduce maybe some oxygens in there, or indeed if we make our materials entirely from maybe starch, we'll find that they're going to break down a little bit more readily for us. Bioremediation is where we maybe do something with an enzyme. Potentially here, for example, we've altered its active site so that another substrate fits into it, and that can then be oxidized or in some way catalyzed so that its removal from the environment is better or easier. So bioremediation is using enzymes for maybe not their initial intended purpose, but we're helping to maybe clean up some sort of polluted site. And the final one, green chemistry, is a kind of overarching idea where we're always concentrating on having a positive benefit to the environment, or certainly limiting our impact on the environment. One aspect of that would be atom economy. And the atom economy is defined as the mass of the desired product from the reaction to how much are you getting of the actual thing. If you just add up their atomic mass numbers, you can work out that, versus how much total products do you get. So an example can be seen here. And if you ask yourself, what's the atom economy for making hydrogen? So we're trying to make this, and this is the reaction that we're going to do. You can see, well, I'm getting 4 out of a total of 48. So my atom economy is 8.3%. So it's a rather inefficient rating there. Also with green chemistry, we're looking at maybe thinking about what temperatures are we running our reactions at. Can we use enzymes to help us lower reaction temperatures, and some of the other ideas we've already met, such as bioplastics.